Automatic generation control is a vital component of modern power system operations, designed to maintain system frequency and power exchange between control areas within desired limits by automatically adjusting the output of multiple generators. AGC works by monitoring system parameters such as frequency and tie line flows and sending control signals to generators to correct any deviations from scheduled values. There are several types of AGC schemes, including centralized control, decentralized control, and distributed or hierarchical control systems. Centralized AGC involves a single control center managing the generation of multiple units, while decentralized systems allow local control with minimal central coordination. Distributed control, often used in large or smart grid systems, integrates both local and central decision-making layers. The advantages of AGC include improved system reliability, enhanced frequency stability, better inter-area power flow management, efficient economic dispatch of generating units, and reduced need for manual operator intervention. However, disadvantages may include complexity in system design and communication infrastructure, higher costs of implementation, and challenges in integrating AGC with legacy equipment or non-conventional generation sources. In the context of today's power systems with high inverter-based renewable penetration such as solar PV and wind, AGC has become even more crucial. IBRs lack natural inertia and have variable outputs, which can lead to rapid frequency fluctuations and system imbalances. AGC helps mitigate these effects by enabling fast, automated response from controllable generation or grid-supporting IBRs, ensuring frequency stability and maintaining reliable operations. Hence, AGC is a key enabler in transitioning to cleaner energy while upholding power system security and performance. AGC is a real-time control mechanism in power systems that continuously adjusts the output of multiple generators. Its main mission is to balance generation and load so that the system frequency stays near its nominal value, typically 50 or 60 Hz, and the power exchanged via tie lines with neighboring control areas remains as scheduled. In effect, AGC acts as the grid's balancing act by rapidly compensating for load fluctuations, renewable output variability, or even generator outages. The system accomplishes this through a closed-loop feedback process where measurements, frequency, power flows, and generation outputs are continuously compared with set points, and corrective signals are automatically dispatched to the generators. AGC definition and the role of ACE. AGC automatic generation control is an integrated, computer-based system that adjusts the power outputs of generators in multiple plants if needed to ensure that the total generation matches the instantaneous demand. By doing so, AGC maintains overall system stability and minimizes deviations in both frequency and scheduled power interchanges. Area control error, ACE, is the key error signal in AGC. It is computed as the combination of two components, the difference between actual and scheduled net power interchange, i.e., difference in the tie line flows, and a term proportional to the frequency deviation from nominal, often weighted by a frequency bias factor. The AGC's goal is to drive ACE to zero, ensuring both proper power exchanges and stable frequency. ACE's impact on AGC. ACE is central to how AGC operates. Positive ACE indicates that the area is overgenerated or exporting more power than scheduled, along with a possible frequency rise. In response, AGC instructs generators to reduce output. Negative ACE suggests undergeneration or importing more power than planned and a likely frequency drop. AGC then calls for an increase in generation. By continuously making adjustments to drive ACE towards zero, the system effectively balances the load generation difference and stabilizes the overall grid. AGC operating functions. The main functions integrated into AGC include monitoring, tracking the frequency, generator output, and tie line flows. Error calculation, using measured data to compute ACE. Control signal dispatch, sending commands typically through SCADA and digital control loops to generator governors. Feedback and tuning, continuously adjusting the gain and participation factors using methods such as proportional integral control so that the control response is both prompt and smooth, minimizing overshoot or oscillations. These functions ensure that both fast transient disturbances and longer-term load changes are managed effectively. Power plant generation dispatcher interaction. AGC bridges the gap between the power plant's operational units and the central dispatch. In practice, dispatchers use economic and operational criteria to set generation schedules and tie line power targets. AGC translates these targets into real-time control actions. It receives inputs from the Energy Management System (EMS) and uses them to send proper control signals to generation units. This interaction ensures that while the dispatcher may optimize the overall generation mix for economic efficiency through economic dispatch processes, the AGC fine-tunes the instantaneous generation to counteract fluctuations, thereby maintaining system stability and the contractual interchange levels. AGC unit response: when a control signal is received, individual generation units adjust their output via their turbine governors or inverter controllers. Each unit's inherent dynamics, including inertia, ramp rate capability, and droop characteristics, play a role in how quickly and accurately it can respond. The aggregate response of all controlled units produces a smooth modification of the total power output, helping to promptly correct any imbalance or restore the system frequency. Common AGC operation modes: AGC systems can operate in various modes depending on the control objectives. Constant net interchange: the system actively maintains the scheduled net power flow across tie lines. Even if local loads vary, the tie line flows are kept constant to honor contractual obligations between control areas. Constant frequency control: in this mode, maintaining the system frequency is the sole focus. Generator outputs are adjusted strictly to counteract frequency deviations, sometimes at the expense of temporary tie line errors. Tie line bias control: this mode blends both objectives by considering a bias factor. The control error is a linear combination of frequency deviations and tie line power errors, meaning that both parameters guide the control actions. The frequency bias factor here is critical for ensuring that the control action appropriately reflects the grid sensitivity to frequency changes. AGC control parameters: some of the critical control parameters that guide AGC operation are participation factors, dictate how much each unit contributes to the overall control effort. Ramping limits: ensure that units increase or decrease output at a safe and manageable rate. Frequency bias factor determines how strongly frequency deviations influence the control signal. Minimum and maximum generation levels bound the control actions to prevent overloading or underutilizing the resources. Gain settings and hysteresis fine-tune the response to avoid excessive oscillatory behavior near the set points. These parameters are calibrated based on the dynamic characteristics of the power system and the specific performance requirements of the grid. Constant net interchange: this operation concept establishes that the net power exchanged over the tie lines should remain at a predetermined value. Even when local load demand changes, the interchange is held constant by adjusting the generation accordingly. Maintaining constant net interchange is essential in interconnected systems, ensuring that power trading and contractual obligations between regions are respected.